Hi, my name is Kwon Liu from Post-Tech Computer Vision Lab. Thank you for your interest in our paper. We introduce LiDomAug, the instant domain augmentation for LiDAR semantic segmentation. Our augmentation method is a novel approach for LiDAR augmentation in the semantic segmentation task. It allows the creation of new LiDAR scans with arbitrary configurations, mounting poses, and motions of the moving platform. Furthermore, our module is designed with an online augmentation method, enabling it to run fast and seamlessly integrated into the data loader within the learning framework. Our approach enhances the generalized performance of the semantic segmentation approach without requiring access to the target dataset. These are the overview of our method. For the input scans, we use the labeled and unlabeled surrounding LiDAR frames to augment the LiDAR. There are 4 steps to augment the LiDAR scans. First, we construct a 3D world model using the surrounding frames. We aggregate the nearest frames from the 3D world model, taking into account dynamic objects and propagate the unlabeled data. Our object is to densify the environments of the input frame by constructing a 3D world model. To achieve this densification, we apply 2 techniques. One aspect is handling dynamic objects. During the densification of our model, we consider the aggregation of dynamic objects if there are bounding boxes annotation available. We track each dynamic object to aggregate them from the surrounding frames into a single frame. Another technique is checking label consistency and propagating the unlabeled data. We aggregate the unlabeled data using a transformation matrix. Since we lack labels for the unlabeled data, we propagate the labels through the voxel majority selection. Within a single voxel, the unlabeled points are assigned the most common label among the points. As a result, we have dense world model for each frame. We pre-compute this and resample from the dense world model in augmentation module. The next step is creating the range map with random LiDAR configuration with pose augmentation. The LiDAR dataset provides a fixed trajectory that cannot be altered. However, since we have already reconstructed the 3D world model, we can generate LiDAR scans as if they were captured from arbitrary poses. Our proposed pose augmentation is simple. We translate the frames from the center to the desired pose before projecting them into the range map. The video demonstrated the difference between the pose augmentation is applied or not. After translating to the arbitrary pose, LiDomAug generates the range maps with randomized LiDAR configurations. Using the moved 3D dense world model, we resample points with an arbitrary vertical field of view, horizontal sampling points, and LiDAR channels. We project the range map using spherical coordinates and sampling points using the jet buffer techniques. As a result, we can resample arbitrary LiDARs that are not limited to the specific configurations. We also add some motion distortion from the moving vehicle. Cylindrical LiDAR exhibit a spinning motion at a fixed rate to capture omnidirectional data. Additionally, LiDARs are commonly mounted on the moving platforms such as vehicles. The combined motions of the vehicle and the spinning LiDAR introduces distortion in the captured frames. We observe this distortion in the real LiDAR frames and make slightly adjustments to the spherical coordinates and depth into account for the distortion. Finally, we mix 2 scenes from the generated LiDAR frames. Once the range maps are rendered with random LiDAR configurations, we combine them by utilizing random azimuth angle ranges and project to the 3D coordinate space. This mixing process enhances data-driven approaches by providing diverse LiDAR patterns in a single batch, reducing efforts to keep a large batch size. Our method shows consistent improvement by a large margin over the state-of-the-art methods in SemanticKITTI to nuScenes adaptation settings. With our domain adaptation method and simple augmentation methods, ours shows better performance than the others. Especially trained on sparse data than the target domain, our augmentation method provides more density buried examples than what is available in source domain, which helps improve the learning of sensor-agnostic representations. These are the qualitative results of the cross-dataset evaluation. The red points are the points that model predict the wrong label. We also present evaluation results on various LiDAR patterns of a model trained on specific LiDAR patterns. As a remedy for the sense bias issues, we propose to train models with LiDomAug using randomized LiDAR configurations. Compared with training original data, our model gets to learn sensor-agnostic representations since LiDomAug provides various LiDAR patterns with realistic distortions. These are the qualitative examples that train and test in synthetic SemanticKITTI. Note that this experiment shows sensor bias is critical to generalized prediction, and our method helps alleviate the sensor bias. More experience and results are in our paper, supplementary material, and our poster sessions. Thanks for watching.